In the chapter so far, we have proven that projective varieties are pre-varieties by covering them with some affine patches. But we haven't yet proven that they are varieties, in other words, that they are separated. And so if you recall, for separatedness, what we need to do is we need to understand the diagonal here inside the product of x cross x. And in fact, since we know that each sub-pre-variety of a variety is a variety, it suffices to show that Pn is a variety, because then any projective variety is closed in there, and so it's also a variety. So really, what we need to understand is the diagonal of Pn, projective space. And to do that, below, what we do is we embed the product Pn cross Pn into some bigger projective space, and then this gives us coordinates to write down the equations for this diagonal. And in fact, we can do this a bit more generally. We can't just embed Pn cross Pn, but in fact, we can embed a product Pn cross Pm inside a big projective space. And this goes via the so-called Segre embedding. So we consider one Pn with coordinates x0 up to xn, and one Pm with coordinates y0 up to yn. And then we set this big N to be this product minus 1. And then we can, on this big Pn, can take coordinates denoted by zij, where I and j run as before. And then we can write down a nice map f from this product here. And then this should be M. From this product here to big Pn, which takes such a tuple here of xi and yj, and then maps it to the coordinate zij equals to xi times yj. So for each pair of coordinates, we record the product of this pair once. And the first small observation is that this is a well-defined map. If we choose a different representative, we scale, for example, the xi by some lambda, then all the zij are also scaled by the same lambda, and so we get the same point in P big N, and similarly for y. So this is a well-defined map, and the proposition here, and you see it also does what we want. It takes a product of projective spaces and gets it into some bigger projective space. And then the proposition here is, first of all, that the image of this map is a projective variety, and we can cut it out explicitly. It's the vanishing locus of these polynomials, and now we have to be careful. It's zij times zkl minus, and then you swap indices, zil and zkj. So you swap basically j and l here. And this holds for all possible indices here. So the image is a projective variety, and then in fact in B we upgrade this and say that this map from here to its image is an isomorphism of pre-varieties, let's say. In particular, so somehow this is closed inside here. This is an isomorphism. We have already seen this. This means that F is a closed embedding. And therefore it deserves to be called the Segre embedding. And for the proof, so somehow the points in the image of F, first of all, we should check that this image here is contained in this vanishing locus, right? One containment. And so if we calculate this equation here on the image of F, well, we plug in the definition and we get xiyj minus xkyl, and then minus this here. And well, we swap these two indices, but of course, the product is commutative. So this indeed gives 0. So certainly F lands inside this, this variety here. And on the other hand, we can look so somehow assume that that zij satisfy all of these conditions. And then now we really want to go to an affine patch and check coordinates there. So what we can do is we can assume one of these coordinates must be non-zero, because this is an element of a projective space. And so let's say that z0, 0 is not equal to 0. And then we can look at an affine chart here, where it's exactly the locus where this is non-zero inside this big projective space, and we study what F does there. And this corresponds, I mean, going into this affine chart corresponds to setting z0, 0 equals 1 in the equations. the dehomogenization. And so in other words, if we take these equations here and put z 0, 0 to be 1, then I guess we choose here k and l to be 0 and 0, and we look at just that equation, then we see here z0, 0, which is 1 times zij, is equal to this product here. Okay, and this gives us already an idea, because somehow in the definition of f, we had that zij is the product of two numbers depending on I and j. So if we set xi to be zi0 and yj to be z0j, then this equation here just tells us, well, that this point that we started with is in the image of f. Let me just f of exactly these two tuples. And so we proved the converse equality. If we are in this affine patch and if we satisfy the equations, then we are in F. And since these affine patches cover everything, we're done. So we have proven the image of F is this projective variety. And then to check that F is a morphism, well, first of all, note the inverse of this U00. So somehow we have Z00 should not be 0. Well, Z00 is the product of x0 times y0. So this is non-zero if and only if these two numbers are non-zero. So the preimage of this affine patch is actually a product of affine patches on the two factors, x and y, or Pn and Pm. And then in these affine coordinates that we have now, we have x1 up to xn and y1 up to ym. And then in these affine coordinates from here to u00, the map just takes this tuple. And then, well, we have these zi0s where we multiply these things with 1, y0 equals 1. And then we have some coordinates where we multiply the yi's, the yj's by x0, namely 1. And then we have these mixed products here as before. And so in these affine coordinates, the map has a very simple form. And then first of all, we observe F is an injective map, because from this image, we can recover these coordinates just by projecting on the first n plus m coordinates, like this. So it's injective. And then both F and this inverse map, this projection map, are morphisms. Because, I mean, here, this is an affine variety, this is affine varieties. And then we just see that this map is given by polynomials in the coordinates. And we have seen this is a criterion for being a morphism of affine varieties. Similarly, the projection map is also such a polynomial map. So both maps are morphisms and they're inverse to each other. So F is an isomorphism onto its image. Okay. So we have embedded the product of projective spaces into a big projective space. We can look at an example how this works. This is the Segre embedding of basically the simplest case, P1 cross P1. And there it says this is isomorphic to something in, this is the big projective space that we embedded in. And the single equation that we look at is 0, 0, 1, 1 equals 1, 0, and then 0, 1 here from the indices. And this is exactly the image of the Segre embedding, which takes these 2 points and maps it to all these possible products. And so if you want to have a geometric picture, you can kind of draw again the real picture. So an affine patch of P1 cross P1 just looks like A2, so it looks like a plane. And then an affine patch of P3, this is somehow A3. And then you can look at the solutions to this quadratic equation, and this turns out to be such a hyperbola, essentially. And then F maps exactly somehow these two kinds of lines are also illustrated here, maps to the surface that is cut out here. And you can, if you want, you can verify again by hand in this small example the things that we proved more generally before. So this is the Segre embedding of P1 cross P1. And then we have, as a corollary, the thing that we wanted to prove, namely that every projective variety is a variety, making sense of the name afterwards. So somehow what we know is that every projective variety is a closed subfree variety of some Pn. So as mentioned before, it suffices to show that Pn is separated. And then we look at the diagonal. We need to show this diagonal is closed inside the product Pn cross Pn. So it's the set of all such tuples here such that these two agree inside Pn. And the claim now is that these two agreeing in Pn is equivalent to this condition here, that xi times yj is equal to xj times yi for all I and j. And to prove that here, to prove that claim, note that these cross products here are exactly the 2 cross 2 minors of this matrix here. Right, so because somehow 2 cross 2 minus means you choose some I and some j, and then this xi minus yj, xi times yj minus xj times yi, this is exactly this determinant of this 2 cross 2 submatrix. And so these conditions are equivalent to the minors of this matrix vanishing. But then by linear algebra, the minors of the matrix vanishing means exactly that the determinant that the rank of this matrix is at most 1. So in other words, the rows of this matrix are linearly dependent, but somehow the 2 rows are both non-zero because these are elements of the projective space. So they being linearly dependent just means one is a scalar multiple of the other, and this is equivalent to these 2 points in Pn being the same point. So this justifies that this diagonal is really cut out by these equations. But now, these equations look very familiar after the proof before, because we can see, Pn cross Pn sits by the Segre embedding in some big projective space, and then the diagonal cut out by these equations. But this here is just f of, this is the zij coordinate of f, and this is the zji coordinate of f. And so, in other words, this here is just a pre-image of this vanishing locus of zij minus zji. So these things are also called Segre coordinates, and then this difference of these Segre coordinates cuts out the diagonal inside this product. And so since this thing here is closed inside Pn, and f is a morphism, so it's continuous, so the pre-image of this is also closed, and then we're done. So it was really helpful for understanding this diagonal, that we could embed it into some known easy space, like a big projective space. And then there we had equations cutting out the diagonal by the pre-image. And then a final remark here is that if x inside Pn and y inside Pm are projective varieties, then, well, we have seen the product of 2 closed embeddings is a closed embedding. So this sits a closed subvariety in this product. And then this here by the Segre embedding sits as a closed subvariety in Pn. And so in particular, this sits inside some big projective space. And so it is a projective variety. And that's something we didn't really know before, right? We had seen that the product of affine varieties was affine, but now we have also seen that the product of projective varieties is projective. Okay, and this was possible via this Segre embedding.